want to talk about the mean value theorem and how to use the mean value theorem to prove other results. Okay. So here is the topic is about the 4.3, and we are almost done. Okay, and I hope we can finish this topic next, as these all the required topics next week. Then the last week you will have your whole week to finish the final exam. Mean value theorem. Okay, and so now let's look at, before that, I want to recall some definitions. Okay, recall some definitions. So we say if x0 in the domain I is called a maximizer, for f, if f of x0 is greater than or equal to f of x for all x in I. Okay, so this is called a maximizer. So we say that x0 is in I is called a minimizer for f if f of x0 is always less than or equal to f of x for all x in I. Okay. So now let's look at the lemma we have, the first lemma. 4.16. So we let I be a neighborhood of x0. And suppose f, which is differentiable, at x0. Okay. If x0 is a maximizer, okay, or minimizer, then this derivative of f at x0 must be 0. Okay. So from the graph, if you look at the graph to understand this one, this is the it's differentiable. For example, here, right? So this is the x0. This is the maximizer, right? So it's always be 0, right? The derivative means the slope of the tangent line. And this is another x0. This is the minimizer. So you can see the horizontal tangent line at this point, right? So the derivative should be 0. So this is the things we have learned in the calculus, right? Calculus 1. So now I want to prove it. Okay, if x0 is a maximizer or minimizer, then the derivative must be 0. So in my proof, I just proved the case that x0 is the maximizer. Then you can use the almost the same strategy for the minimizer. Okay. So now let's look at the proof. So since I is a neighborhood of x0. Okay, so what's the meaning for the neighborhood? I can draw the picture here. If this is x0, sorry, This is the x0, right? The neighborhood is this one, right? The open intervals containing this point. This is called a neighborhood. Then there exists some epsilon greater than 0 such that this x0 minus epsilon and x0 plus epsilon, this interval, we must have this interval, right? This point is x0 minus epsilon, right? This point is x0 minus epsilon. This point is x0 plus epsilon. So this is the x0 is the center of this interval, right? So this interval must be inside. We can find this one, right? Okay. Then we take an is equal to x0 minus epsilon over n. Okay. So which means must be inside this intervals, right? Here is epsilon. From here to here is epsilon. So minus x0 minus epsilon over n would be here, right? Between. And Bn is equal to x0 plus epsilon, right? Over n. So this, if we take these numbers, okay, An and Bn will approach x0 when n approaches infinity, right? And this An and Bn are not equal to x0. Of course, they're not equal to, because epsilon is not 0, right? N is not 0. So this An and Bn are not epsilon, x0. Then we can use the definition about the differentiability. Since f is differentiable if at x0, then the derivative at x0, which is given by the limit x approaches x0, f of x minus f of x0 over x minus x0, right? This is the definition. Okay. So now this x approaches x0. So if we take the we know An will also approaches x0. So we have the limit An, which is n approaches infinity, f of An minus f of x0, An minus x0, right? No matter what x is, right? We just need x approaches x0. Okay, so now we replace x with An. So let n approaches infinity. When n approaches infinity, this An will approaches x0. So in other words, this difference quotient must be, take the limit, must be equal to f prime of x0, right? Okay. On the other hand, if we replace x with Bn, because Bn will also approaches x0, right? So the limit means the if you take the arbitrary sequence, right, which will approaches x0, then this limit, they have the same numbers, right? Okay, this is x0. Then you take the limit, n approaches infinity. So this Bn will approach x0, this Bn will approach x0, but from this one, it's equal to f prime of x0, right? Okay, so both get the same number, because the reason is this limit equals this one, right? It's differentiable. So now we want to show this one is equal to 0. So before that, let's look at, we note that an minus x0. What is an? An is equal to x0 minus epsilon over n. So this an minus x0 would be equal to negative epsilon over n, so which is negative number, right? And bn minus x0 would be epsilon over n, which is a positive number, so it's greater than 0. The bn minus epsilon. Okay. Since, so this is the difference for the maximizer and the minimizer here. If x is maximizer, okay, so if we only prove for the case x is a maximizer, so for the minimizer, you can change a little bit here, right? If a is x0 is a maximizer, then that means f of an minus f of x0. So this is the maximizer. So this is the maximum value. So it would be less than equal to 0, right? So in other words, the f of an minus f of x0 over an minus x0. So this one is less than 0. This one is less than equal to 0. So it would be positive, right? Non-negative, greater than equal to 0, right? So this one is greater than equal to 0. Then if we take the limit, then the limit will have the proposition, right? In the we have the lemma. If you don't know that, you can go back to check. Lemma 2.21. It says, okay, the limit is still greater than equal to 0. Similarly, we can show that using the similar way. We can show that this f, sorry, here is not epsilon 0, here is x0. F of bn minus f of x0 over bn minus x0 would be less than equal to 0. Okay, then we can get the limit n approaches infinity of f of bn minus f of xn x0 bn minus x0. This limit would be less than equal to 0. If you put together, because they are the same right, same number. So the only choice, so the same number, this number is greater than equal to 0. The same number, which should be less than equal to 0. So this the only choice is equal to 0, right? So we get this one. Then similarly, for the case x is a minimizer. Okay, so the minimizer, then this would be changed, right? This would be greater than equal to 0, and this would be less than equal. Then you use the similar way, right? And this would be less than equal to 0, and here would be greater than equal to 0. Okay. Any questions? Okay. So this is the one of the rules we use when we do the optimization problem in the calculus, right? So this lemma tells you that the minimizer and the maximizer only happens at the derivative equals 0. We know we call the name x0, which is make the derivative equal 0, which is called what? Which is called the critical points, right? So in other words, the maximizer and the minimizer only happens at the critical points. This is the thing we use here, right? And another good thing is, for this lemma, the good thing for this lemma is we didn't need a lot of requirements, right? You can see that we just, what we need is just f is differentiable at this point at x0. We don't require other other requirement. We just need differentiability. Okay. So now let's look at this theorem. 4.17, which is called the Rolle's theorem. Suppose f, which is from a closed interval AB to R, this function f is continuous on the closed interval and differentiable on the open interval. If f of a, the endpoints have the same function values equals f, then there exists some x0 which is between a and b such that f prime of x0 is equal to 0, right? From the graph, right? This is A and this is B, right? We must have some point here. This is the x0 such that this is the tangent line, which is a horizontal at this point. Okay, so this is the geometric description. Okay, so let's prove it. So we know that if a function is continuous on a closed interval, that means we can obtain the maximum values and the minimum values, right? So this is by the extreme value theorem tells us f can attain its maximum and minimum on this interval AB, closed interval AB. Okay, so now let's look at the different cases. Case 1. If both values, the maximum values and the minimum values, means both values happen at the endpoints. So A gives you the maximum value, B also gives you the minimum values. Okay, so that means since f of A is equal to f of B, right? So in other words, the maximum values is equal to the minimum values. So that means on the whole interval f of x on this interval AB must be a constant, right? The reason is the maximum values are equal to the minimum value. The maximum is equal to the minimum. Okay, it's constant, so the derivative is equal to 0 for all x in AB. Of course, there exists someone, just pick arbitrary one, right? So for this case, it's obvious. Let's look at the next case. Next case says, okay, at least one of these two values occurs at somewhere between A and B. Okay, that's case 2. At least, then we conclude all the cases, right? At least one of these two values, the maximum value and the minimum value, okay, occurs at some x0 between A and B. Okay, sum x0 between a and b. So we know it's inside, it's differentiable. So we just use this lemma, tells you, okay, if it's differentiable at x0, then if x0, because one of the values means the maximum value or the minimum value. So x0 must be the maximizer or the minimizer, right? Then this lemma tells you this derivative must be 0. Okay. So case 2, so then the lemma 4.16 shows us this f prime at x0 must be equal to 0. There we are done, right? We consider all the cases. So this is the Rolle's theorem. Okay, so now let's look at the mean value theorem. So actually the Rolle theorem is the special case for the mean value theorem, but here we need to use the Rolle theorem to prove the mean value theorem, okay, which is called this for mean value theorem, mean value theorem. If f is continuous, conditions are very similar on AB and differentiable on the co-open interval AB, then there exists some x0 between A and B such that f prime of x0 is equal to f of B minus f of A over B minus A. Okay, so this is the, let's use the graph to tell you what's the meaning for it. Okay, so this is the A, this point is A, f of A, right? This point is B, f of B. Okay, if you connect these 2 points to form a signal line, a line segment, this line have the slope m, which is equal to f of B minus f of A over B minus A. Okay, so this is this one, right? This is the slope for this line. So this theorem tells you that you must have some points, okay, x0 here. The derivative of this x0 at this point, which is the same as this number. So in other words, the tangent line through this point should be parallel to this dashed line here. They have the same slope. Okay, so this is the geometric meaning. So now let's prove it. Okay, the proof is a constructive proof. It's not easy, but when you construct this function, everything becomes very obvious. We define a function hx, okay, h function, which is f of x minus mx, m times x, such that h of a, when x equals a, is equal to when x equals b. Right? We want to construct this kind of function to make this one to be true, because we want to use the Rolle theorem. Then we can use the Rolle theorem on this one, right? So what is the m we choose? Which m we should choose? Okay, So it says, okay, so f of a is equal to, so f of a minus m times a should be equal to f of b minus m times b, right? Then you solve for m, so m should be equal to f of b minus f of a over b minus a. Okay? If we take this one, then we satisfy this condition. Okay, so now we can apply the row theorem to this function h. Okay, because this h is differentiable, no problem, you can take the derivative, right? Because f is differentiable. This is a linear function, of course, you can take the derivative. Then this is the only requirements we need, right? It's differentiable and continuous, of course, it's continuous. Right, this is continuous, this is continuous, so it's plus together would be continuous. So we can use the row theorem, okay, and HA equals HB. So apply this, so there exists some x0 between A and B, such that the derivative of h at x0, which is equal to 0. So we have, what does this mean? H is equal to f minus mx. So we take the derivative. So it would be f prime minus m is equal to 0. So f prime of x0 is equal to m. So what is m? M is we have to choose this m, b minus a. Then we are done. Right. So the mean value theorem is very useful. So this is the mean value theorem. It's one of the key tools for turning information about the derivative. This is the derivative, okay, of a function into some information about the geometry on the graph. So why it's called geometry? Because this represents the slope, right? Okay. So this is a very, very useful theorem. So we can use this theorem to prove a lot of things. Now let's look at some applications for the mean value theorem. Applications for the mean value theorem, which is the lemma 4.19. If f, which is from I to R, is differentiable on I, then f is a constant if and only if f prime equals 0 for all x in I. Okay, if so f, so this is the if and only if problem. So we needed to prove two directions. Okay, so this direction, if f is a constant, then the derivative equals 0. Yes, of course. Right, this is from the rules we have. Right, this is obvious. Obvious result. The other way. So suppose we have a function f prime of x equals 0, which this is true on the whole interval. for all x in I. Then we want to show that this on this I, interval I, this function must be a constant function. Okay, so the idea is, so since I is a open interval, right? This is the open interval. This is the open interval. So now let's pick arbitrary any two values, x1 and x2, which is in I. So the idea is we want to show that this f of x1 is equal to f of x2, right? Because since they are arbitrary 2 points are equal, so everything is equal on the whole interval, right? Of course, we can assume that x1 is less than x2. Okay, this is without loss of generality. So since these 2 points are in I is an interval, so this one, x1 from x1 to x2, which is inside this one. Okay, then we apply the mean value theorem to this interval from x1 to x2 on this interval, not on I, okay? So then it satisfies all the conditions for the mean value theorem, right? We have applied to this one, then there exists some x0, which is between x1 and x2, okay, which is also inside I, such that f prime of x0 is equal to f of x2 minus f of x1, x2 minus x1, right? Since we know the derivative at any point in I, which is 0, so f prime of x0 must be 0, right? Since this one equal to 0, so that means f of x2 minus f of x1 over x2 minus x1 must be 0. So that means if you have a fraction equal to 0, the x1 is not equal to x2, right? Because we know x1 is less than equal to x2, less than x2. So that gives you that the numerator must be 0. So f of 2 equals f of 1. Right. Since x1 and x2 are arbitrary. On I. Then f of x must be a constant on I. Then we're done. Okay. So this gives you some ideas, okay? When you have a constant, the derivative equals 0. If the derivative equals 0 on the whole interval, then it must be a constant function, right? This is a very important result we use a lot, right? When you have a derivative equals 0, the first thing you can think about is, okay, this function must be a constant function. Proposition 4.20, which is called identity criterion. Suppose function g and the function h are differentiable on an open interval I. And this is the only condition we have. Then the result is g prime equal to h prime on I, on the whole interval I, if and only if G is equal to h of x plus a constant C, where C is a constant. Okay, so it says this this proposition tells us that if you have two functions that are differentiable on the same intervals, if the derivative are equal on the whole interval, then these two functions, the difference between these two functions must be a constant. Okay, this theorem, this proposition is very useful for the differential equations, right? This is the foundations of the differential equations. If you have some two functions, okay, you have so that means if you have no any restrictions, you have many. If the derivative are equal, then the solution you have infinitely, because C could be any constant, right? So you have infinitely many solutions. So you should impose some additional conditions to make this C to be unique. This is the topics in the differential equations. Okay. So now let's prove. Prove is, so this time we don't want to one side and the other side. We want to hold this one. We want to prove at both sides as simultaneously. Okay, at the same time. So we have we let f of x equals gx minus h of x. Okay. So we have the lemma says, okay, f of x equals a constant, C is a constant, if and only if the derivative must be 0. Okay? So this is the lemma we just proved, 4.19. It's equal to constant if and only if the derivative equals 0. So the derivative equals 0, that means g prime is equal to h prime, right? Because f, take the derivative, g prime minus h prime equals 0, so g prime equals to h. So what's this? This is fx equals c, that means gx plus equals h of x plus c, right? So we are done, right? We have this one, if and only if and only if and only if, this one. So this is the end of the proof. Okay. So there is a very important, you may not focus on this fact. This is only true for it's differentiable on the interval. Okay. This domain must be an interval. This is the only things you may not be pay attention. It's differentiable on the whole interval. This domain must be an interval. Okay. So if the domain is not an interval, then it may not be true. For example, let's look at the remark. Okay, we have two functions. F of x equals natural log the absolute value of x, right? We have another function, g of x, which is equal to ln natural log of x. When x is greater than 0, natural log of negative x plus 2 when x is less than 0. So you can say these two functions are exactly not the same thing, right? They are not equal. They are even different. Okay. So the domain for both functions is R except 0. So this is not an interval, right? And we notice that if we take the derivative, g prime of x, which would be equal to f prime of x on this interval. Okay. Then these two functions are not the same. F and g are not the same. Of course, yeah, they are not the same. Okay, so this is the one thing we have talked. Okay, so we stop here. Okay, so next time we want to continue this topic a little bit and then go to the next section. Any questions?
No, sir.
Okay, thank you.